Welcome to our project, Biomedical Seizure Detection. We are a team from Faculty of Engineering, Cairo University. In our project, we are using machine learning algorithm, Gilbert's algorithm, to detect seizure. Before getting into details, let's have a brief introduction about seizure. Seizure is an unpredictable neurological disorder caused by structural abnormalities in the brain that may have a severe effect on the quality of patient's life. According to statistics in 2015, more than 50 million individuals are diagnosed with epilepsy. That's why we're interested to be part of the solution. After reading the EEG signals from the patient's brain, which provides measurements of the electric activities in the brain, we retrieved data set from the EEG signal to be used in training the algorithm. This is an example of the EEG signal indicating the period of seizure. Ictal period is our main focus in our project. Problem definition. Since machine learning is all about training the machine to do a certain function, in our case, we're classifying between two classes, seizure and non-seizure. And this is done by using Gilbert's algorithm.
We will be talking about Gilbert's algorithm. So basically, Gilbert's algorithm uses geometrical approach to the SVM training problem. What's meant by geometrical approach is that we use math on shapes, or Minkowski's difference. Minkowski difference simply is if we have those two classes, class A and class B. We take every point at A and subtract it from B to get A minus B, the yellow shape. Now we can observe that if either of the radii increased, the yellow shape radius increased accordingly. But it's more important that if the two classes get intersected, the yellow shape includes the origin point. We can use this fact in the training of SVM that if the two classes get so close to each other, the two closest points on the opposing classes maps to the closest point to the origin on their Minkowski difference. The projection of this algorithm on the training of SVM is described here. Suppose that we have those two classes and we want to get the two closest points to get the maximum margin classification. We find the Minkowski difference of those two classes and start searching for the point closest to origin on their Minkowski difference. Once we get there, we can find the maximum margin. In more details, this can be described as follows. Suppose that this is the Minkowski difference of the two classes. The algorithm first chooses a random point. It then goes at the direction of origin and tries to find the point that's close to origin. Now the algorithm asks himself a question. Which point on the line segment is closest to the origin? Is it the old one? Is it the new one? Or is it a point on the segment? To answer this question, the algorithm calculates these two parameters, which is top and bot. These two parameters are the distance between the origin and the old point, then between the origin and the new point accordingly, respectively. So now if the bot is smaller than top, we can clearly see that the new point was closer to the origin. So the algorithm chooses that this is the next point, and then it iterates and repeats the process, and now it asks the same question. Is it the old point, or is it the bot point? To answer this time, we can observe that the top is smaller than the bot. So we can imagine a circle that has a radius of top and the center of origin. We now measure the excess of the bot from this circle. Take this excess parameter, or this excess factor, from the old point, and now we can find the point on segment that's closest to origin. The algorithm chooses this point and repeats. Now it clearly finds that this will be the closest point to the origin, and it found the algorithm converged. Now the algorithm found the two close points, and now it can easily find the SVM that introduces the maximum margin. Now it's time for our demo show. We have our DE10 nano kit connected to an LCD for easier output observation. As we mentioned before, we are targeting a chip that is able to train SVM and then classify online data. For the simulation scenario, we are assuming that the online data is stored on the FPGA block RAM. We already initialized the memory contents with the test data, and now we are going to simulate its ability to classify. On the MATLAB here, we got the EEG test data as the input wave. We already know that a seizure would occur at the 300 input entry. That's why we played a little trick, and when I go on and press the tactile switch to reset the system, that's located right here, it initializes the memory address to the 300 location, instead of pressing the switch many times, which would have been inconvenient. Now, as I press this button here, which is an incremental button, it's an address incremental button simulating the next entry, we can observe that the FPGA classifies the data according to the waveform here, where we can clearly observe that it successfully classifies this entry, which is the 300 entry, as a seizure point. We can observe the abnormality. We can observe the abnormality of the EEG signal here, indicating a seizure point. It lasts as so for several entries, and this is already shown here by incrementing the address and still deciding it's a seizure point. After several entries, we can now observe that it reset to its normal states, indicating a non-seizure entry.